What I really want to do is focus on problem 2, which is the shear and moment diagrams for this type of problem. Okay. So what we want to do is we want to draw the shear and moment diagram for this overhanging beam. What is the first thing we need to do in this particular problem? Do you remember? And is it big enough on your screen?
Yeah, it's fine. You need to find the reactions at A and C.
Yes. So if we draw a free body diagram, right? So here's the beam. There's a reaction AY. Actually, it's hinged, but there's no X forces, so we don't even have to worry about that. We have 8 kips here. Then we have CY here. And then we do have 2 other forces, right?
Yeah, but they're distributed.
Yep. The one on the right, this one is easier, right? Because that actually acts right here at the center between those 2 points. And what's this? Can someone give me the actual force that we equivalate, I guess, from that distribution? If you multiply by feet, the feet cancel, right?
Oh, it's multiply. Oh, okay.
So it's 8. Yep. And what about this triangle here? This distribution.
Say that it's. Wouldn't it be 6?
6, yeah. So this force, it's a triangle, so it's 1/2 base times height.
Right.
So the base is 6 feet. The top here is 2.
Oh, okay.
Okay. And where does it act? Does it act at the center?
Wouldn't it act a little bit to the right?
Correct. Yeah. It's like it's just like the hydrostatic forces, right? 2/3.
Right.
Holy crap. Everything is coming together, I hope. Cool. I don't know why I wrote kips. I just write kip. So now we have a free body diagram. How do we find the reactions now?
Do a sum of the moments.
Yep. Does everyone understand that?
Yeah.
Sum the moment at Y or A, pick a direction. This will find CY. So let's go, I have -8 kip times 4 feet. Then I have -6 kip times 8 feet plus CY times what? 10 feet minus 8 kip times 12 feet. That equals 0. Am I correct in that moment equation?
Yeah, it looks right.
Makes sense to me.
Okay. It's kind of fun, right? I like doing these in statics. For my favorite moments back then. You're all probably rolling your eyes, but I can't see, so I don't care.
You got me at least, so don't worry about it.
So we end up with 17.6 kip for CY. And then we can just sum the forces, right, in the Y and set it equal to 0. Up is positive. This can find AY. So we have AY minus 8 kip minus 6 kip minus 8 kip plus 17.6 kip. And did I do that correct? 8 negative, negative, positive, yep. And we get 4.4 kip. Okay, cool. Can I keep scrolling up? We good right there?
Yeah.
Okay, now what we need to do is we can now find the equations for the shear forces and the moments throughout this beam. Okay, so I'm going to find V1 and M1. And I'm going to say it's between 0 and 4 feet. Okay. So I'm going to draw the sketch here to remember. This is X1. This is the AY. This is 4.4 kip. Oh, I don't like that. This is V, and this is M. I'll show you back at the sketch. This is located right here. Okay, do you see where that's located on this graph? We're not going to include the 8 kip. Okay, it's everything but that. So we're looking at that section to find the shear and moment diagram equations between there. So we sum the forces in the Y, 4.4 kip minus V equals 0. And along this section, the shear force is 4.4 kip. It's constant. Okay, now we take the moment, set it equal to 0, and it's negative 4.4 kip times X1. Did I pick a direction? This way is positive. Plus M equals 0. We'll just say times X1, and the unit would be kip times a foot. So this moment is any moment created from here all the way to here, just before that negative 8 kip. That's the moment in that section. So just a quick couple things. I don't have this in my notes. I'm winging it.
I'm here. Thank you.
Okay. Yep.
I'll watch like the first 10 minutes of this lecture later.
Yeah, it's pretty much just a review of statics for the first
Okay.
part.
Yeah,
Yep.
I definitely want that.
And then what I did here is, see this purple section right here, this box, this rectangle?
Yeah.
We're looking to find the shear and moments within this section of the beam first, right before this 8 kip is applied. Okay.
Okay.
So what we ended up doing is a free body diagram. That's what the purple is. And over here, the green is we sum the forces to find the shear force, which is constant, which is a line like this. Okay. And then the moment is created along this whole thing. So we can find what the moment is at any point when we define X1, which is linear. So this is linear, so this goes up, right?
Mm-hmm.
So can someone tell me what the slope of that line is?
Is it 4.4?
Yes, it's V, right? So if you take the derivative of the moment with respect to x, it's V. So if you look here, this is horizontal, right? The V versus x. When you have that, it goes to a linear line. Okay, so remember that. So these two equations right now, actually, we could put subscripts on there. This is section 1. And if you want, you could put subscripts over here in the purple. So these two equations, you're going to have to program. Questions before we move on to part 2. Find V2, M2. Here is my sketch. .4 kip. This is 8 kip. Hey, get down. Get down. No. Let's see. This force I'll put here in a minute. No, 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 no. You just ripped it. Here is V2 and M2. And where are we looking here? We're looking between 4 foot and 10 feet. We're going to define X2 from 0 to 6. Okay. That's just how we're going to define our set for X2. No, don't touch that. This distance is going to be X2 over 3, and X2 starts at the 8 kip. So if you go back to the sketch, you can see, and I can draw it on there. I'll go up there and I'll come back. We are now looking at this section right here.
Sir, I don't know if I missed something. Why do you have X2 over 3 there?
That's the distance.
Yep.
So if this distance was what, 6 feet?
Oh, I didn't know. Is it like, are the forces like even between? Like, is it?
No, because this is a triangle.
Okay.
Okay, this is a triangle, so it's actually 1/3 from the right side or 2/3 from the left side.
Oh, I got you. Yep.
This force is actually 1/2 times 2 kip per foot times X2 over 6 times X2. So how do we get when we find the triangle force or that distributed load, it's always the area, right? That we need to find. Does that make sense? What's the area of a triangle? 1/2, right? Base times the height. Okay. Now, when we're looking over here x2 is our base. Okay. So depending on how far we go, that's our base. Okay. We just need to figure out what the height is of that triangle at that certain distance. Okay. So what we can do is if we assign this to be x2, initially this is 6 and this is 2. Because the distribution load, the height, the max was 2. Okay. And the width of that beam we're looking at is 6. We can say y equals mx plus b. We're going to find an equation for that. There's no y-intercept, and I'm going to define this as w, which is delta y over delta x times x2. The slope is really 2 minus 0, 6 minus 0 times x2, which is 2 over 6 times x2. So that's our height. We plug that into here. 1/2 x2 times 2 over 6 x2. Is that what we had there? Over here, if we sum the forces in the y, we have 4.4 kip minus 8 kip minus 1/2 times 2 times x2 over 6 times x2 minus v2 equals 0. So again, just to recap, this 4.4 is right here. This -8 is this graph here. And then this is basically the triangle force equivalent at a certain x along this section here. So this purple arrow actually is kind of moving left to right. And this is kind of that force. Okay, so depending on where you are, the shear force is going to depend on what you get. Okay. So probably technically, I probably should take that off because this arrow kind of moves back and forth depending on where we are for x. Cool. So look, this right here is the shear force between 0 and 6 feet. So now we can do the moment. Set it equal to 0. And we have -4.4. What we have to do, though, is this distance was 4 feet. So we have to add 4 to x2. Because our x2 starts right here on where the 8 kip is. And then we can put our other force, that purple one that moves back and forth, 1/2 times 2 times x2 over 6 times x2. And then what we need to do is this distance is where I just erased x2 over 3. Plus the moment. Because this always acts 1/3 from the right side of your beam. No matter if you say we're only like say x2 is maybe 3. Oh. So if x2 equals 3, it's still acting x2 over 3 from that right side. Okay. So the moment is -x2 cubed over 18 minus 3.6 x2 plus 17.6. So this is kind of cool because, I mean, this is hopefully it's making sense, where this force is basically, depending on how big of the beam we're looking at, will move, but it always acts x2/3 from the end, okay? And when we sum the forces, we can find the shear force. When we sum the moments, okay, we can figure out the moment. Now, what I want you to try is calculus. Find the moment, or sorry, find the moment 2 from this calculus. Do you remember that I showed you this, right? Up here in this. If you take dm dx, that equals v. So how do you find the moment if you know v2? Any guesses? Integrate, right? So dm2 equals v2 dx2. We're going to integrate. So we can integrate v2 to find, technically, if you want, sorry, I didn't put subscript on m2. Let's put a subscript here too. This is m naught 2 to m2. This is v naught 2 to v2. So the reason I'm doing this is because I want to, again, reiterate that knowing the calculus will help yourself just fundamentally understand how things are working. So integrate. Can someone tell me the initial moment at the beginning of section 2 at 0?
Is it just 0?
Right.
It's not 0.
Yes, thank you.
Why is it not 0?
Oh, is it? Because it's like overhanging or something.
Yeah, it's this weekend. It's
Well,
I'm going
if you look here, see this equation, number 1? Actually, we'll call it number 2.
Yeah, it's
It ends right here, right? This right here is the beginning of section 2, correct?
Yeah, and it's already got a value.
And it has a value at there. So the initial value at 2 is going to be the 4.4 kip times the 4 foot. Because if you go back up here, X1 ends this section, and it's technically the beginning of section 2. So that's the initial moment. Does everyone see that? Equals. Oops, I did a big boo-boo. This is not V. This is X naught 2. Where's the head of lettuce? Fix that. Because your limits always are on the right side of the D's. So this is X naught 2, which we defined as 0, and we're going to go to X2. In V2, we plug in minus X2, I think it's squared, over 6 minus 3.6 dx2. I want you to do this integration for me. Try that. Why I give Renner something to play with. He's reading the strengths book.
The moment for what you wrote above.
Yeah, you better get that, right? So over here on the left, it's M2. This is just a 1, right? So when you do the integration, it's actually just M, and then you plug in the top minus the bottom. So M2 minus 4.4 times 4. Over here, it's negative x squared cubed over 3 times 6 minus 3.6 times x2. This is evaluated from 0 to x2. And guess what? When you plug everything in, you get, you gotta be careful, bud. The same exact equation that we had above.
Is this just 2 ways to do it then?
Yes, 2 ways to do it. Yep. I wanted to show you the calculus way because I wanted to show you that this can be done the calculus way, which I don't know if they showed you to do this in strengths, did they?
Joe Riley kind of did at the end, but not really.
Yep.
I don't think so. I think we ran out of time to do anything like that.
Okay.
Then we can use like Sims and MATLAB.
So I'll give you, I think I put on there use Sims, but I'll give you the option if you want to use that or not. Or if you want to do like a case and switch, you can do that too. But again, the cool thing is if you take the derivative of this, like the derivative is you multiply by 3, you subtract 1 and all that stuff, you get back to what you had, okay? Cool beans. So what do we have? How many equations now? We got, go back to the top. This is equation 1. The M1 is equation 2. We got equation 3. And we got equation 4. So 4 equations right now. Find V3, M3. This is between 10 and 14 feet.
Dad, come look what I buy.
And we're going to define X3 from 0 to 4 feet.
Look what I buy, Dad.
Nice. I'll look at it after, okay? So here is pretty much the total beam, the entire beam. But now we're looking at X3. This is where the CY starts, 17.6. This force is 2 times X3. We have V3. We have M3. Oh, let's go over here on the left. We got 4.4 kip. We got 8 kip. And then somewhere here we got, it might be not to scale, but this is the 1/2 times 2 times 6 kip. So just remember, like this section, this will go from basically 0 to 4 feet. So even if we're looking, even if this section was 0 to 1 foot, this free body diagram is exactly true. Okay. If it's 0 to 2, 0 to 3, 0 to 4, it's the same free body diagram on the right because you're looking for the shear force in the moment between 0 and 4 feet. And there's a distributed load that you need to look at. That's why this is a function of X3. So let's sum the forces in the Y. Get a book. We got 4.4 kip minus 8 kip minus 1/2 times 2 times 6 kip plus 17.6 kip minus 2 times x3 kip minus v3 equals 0. Negative 2x3 plus 8. And the units are kip. Because this is equation 5. Didn't do that right. Yeah, I'll just do this way, but if you want to do the calculus way, you now know how to do it. Minus 4.4 what we need to do is we need to say, well, we need to add 10 because that's 10 feet from here to here. Here, something must be. Plus x3 plus 8 kip. This is, you're going to add 6 feet to get to x3 times x3 plus 1/2 times 2 times 6. And this force is 2 feet from point C or x3 plus x3 minus 17.6 times x3 plus, this is always going to be 2 times x3, that's the force, and it always acts halfway between your beginning of x3 to the end of what you pick, plus the moment. Okay, so M3, this is the moment, again, between, if you took any moment between 0 to the end of the beam, so 0 to 4 feet, we would get minus x3 squared plus 8x3 minus 16. This is equation 6. Okay, so we now have 6 equations. You can then plug into MATLAB and program, define your x1, 2, and 3s. So this is technically what you should get when you plug in your equations, okay? And the cool thing is, if you look, hold on, Scarlett. Did he? Okay. The slope of this gives you this. And at each line, if you take the slope of the m versus x, you will get basically how this curve is going to go, okay? And always remember that if you have a straight line here, you're going to get a linear line here. If you get a curved line here, you'll get a more of a curved line at the bottom, okay? Hey, stop. This is linear here, so you're going to get just like the second order there, okay? Now, you're going to see when you do problem 1 with the physics or dynamics, you're going to see those similar trends. Like a linear line goes to, you take the derivative to a horizontal line and so forth, okay?